As you know, in Problem Solving Project 1, you have the choice between 3 different topics. Today, we're going to look at choice number 2, which is Google Trends. And so this is all about the Google Trends Challenge. First, a few words about Google Trends. This is a data source, and it documents search frequency. The data are organized on 3 dimensions. The first is the search term. What kind of information are people looking for? Are they looking for information on a particular news story, on a particular product or service? Whatever it is, there's some kind of term that must be entered into Google to perform the search. Second, there's a time period over which the searches take place. For example, an interval over the previous 24 hours, over the previous 7 days, over the previous year, and so on. The third dimension is geographical area. Search frequency is going to vary depending on the particular location. All data in Google Trends are presented on a scale of 0 to 100. And so this is very important for you as you interpret what you see. 0 doesn't necessarily mean that there was no search activity whatsoever. It simply means that the data have reached their minimum frequency over the given time period. And 100 likewise means that the data have reached their maximum search frequency over the given time period. So this reflects that there are limitations to Google Trends data. Some aspects of Google's search patterns are proprietary and they are company secrets. Today's example is going to concern searches on the Chinese word for pizza, a very pleasant idea, pizza. And we're going to be looking at data over the previous week, from 7 days ago until now. And we're going to focus on searches in the New Taipei area. So why shouldn't we use a longer time frame than just 1 week? There's a good answer for that. We want hourly data. We're particularly interested in looking at how search frequency varies depending on the hour of the day. And this is another limitation of Google Trends. Hourly data are available for periods of up to 7 days only. When you select a longer period, you're going to get less frequent data. For example, you may get daily total search activity rather than hourly. So we're going to do this example in 2 parts. First of all, we want to present a basic example, and this is going to use a quadratic polynomial. Now, if you looked at the tutorial on the air pollution challenge, then this is already familiar to you. A quadratic polynomial is a polynomial of degree 2. It's going to be a parabola, and a parabola can have either 1 minimum or 1 maximum. So this is a very basic example that will allow you to identify that minimum or maximum. However, this kind of basic trend has some limitations. Higher order polynomials don't work so well with Google Trends data. There are times when you may want to look for more than just 1 minimum or maximum, but you'll find that if you go to a higher order polynomial with this Google Trends data, there may be problems with that. And we're going to explain why this is so. So what are you going to do if you're not satisfied with the results of your quadratic polynomial analysis? Maybe you feel like you can do more with your data. For this case, we're going to present a more advanced example using sines and cosines. So maybe you worked with this kind of function when you were in high school, and here they are again. They're very useful for this type of analysis, and we're going to demonstrate that in the second part of the tutorial. So to keep things clear, we're going to divide the tutorial into two different videos. The first is the basic introduction, which is this video. The second will be the more advanced example, and that will be in a separate video. So there's the address for Google Trends, and let's take a look. Our first step is to enter that search term, which is pizza. And let's just go ahead and press the Explore button. And this graph right here shows data for all of Taiwan for searching on that term. If we look closely, we can see that this is data over the past 24 hours. And so this is currently now while I'm making the video, and this is one day beforehand, 24 hours beforehand. We need to change the setting here. We're going to go from the past day to the past 7 days. Okay, and we also want to change the location. As I said before, we want to go to New Taipei City. So I'm going to click on this location here. And so now it says New Taipei City, and there is the graph. If we click the down arrow, we'll get a CSV file with all of the data points inside. And so let's open it up. And we're going to do a couple things to straighten this up so we can use it. First of all, we don't really need these top two rows here, so I'm going to delete them. And we don't have the right Chinese term there, so I'm just going to paste that in. I always like to freeze panes, and so I'm putting my cursor right here in cell B2. I'm going to go to the View tab and freeze panes. So this is going to allow me to go up and down in the file and still see the captions there, which is very convenient. Now, before I do anything else, I really should save the file to a different format. It's now a CSV file. However, if I want to put any kind of formulas in here, then they can't really be saved well as a CSV format. I need to save this to an Excel format file. So I'm going over to a folder, and I'm going to change the format to Excel, and I'm going to call this Pizza 2. I already have another file there, but we're going to use this one right here, Pizza. Okay, so let's take a look at what's in column A. I'm going to make it a little wider, and we'll see that we have these strings here. They're kind of like both the date and the hour of day. Now, this is what the strings look like. Each of these date and time strings has 13 characters, and the last two characters there represent the hour. So the hour is going to be our independent variable. We need to isolate this. We don't want to have the date in there as well. We want to have the hour in a separate column. So I'm going to highlight the B column, insert a new one, and call it hour. Fortunately, there's an easy way to get those last two characters. Excel has a very useful function called write. And it just means that we're going to take the few characters on the right side of the string and copy them. And so we're using A2 as the input, and we're looking at the last two characters there. And there we go, 22. If we pull this down, we'll notice that there's a little bit of a problem here. Okay, at the top we have 22, then 23, and then it looks kind of strange. Instead of getting a 0 and a 1 and a 2, we now have 0, 0, 0, 1, 0, 2, and so on. And so it's pretty clear that we have characters here. We don't really have a number, which is what we need. How do we convert this to a number? The answer is we use the Excel value formula. Okay, so I'm typing in value, and there we go. Here you can have a closer look. Okay, I'm using formula text, and we're looking in cell B2. And you can see we have the right function in the inside, and then we put that into the value function, and we wind up with a number instead of characters. Okay, so I want to do this to my whole column. Now, we have 170 rows here, and so what I'd like to do is go over here to this field, and I'm going to highlight from B2 to B170, and then I'm going to paste this function. There, that's exactly what I need. All right, now there's something else I need to do. I'd like to get a look at the behavior of the hour and the pizza searches. I want to see how they're related to one another in a graph. And so I highlight these two rows right here and then go to Insert, and I need a scatter diagram. Okay, so there it is. There is my scatter diagram. And it's pretty clear that the horizontal axis really does represent time. We have 0 is the minimum value of our independent variable, and 23 is the maximum value. The dependent variable is search frequency, and we already know that that goes from 0 up to 100. That's our maximum. Okay, so let's go ahead and put in a quadratic polynomial. All right, so I'm going to use this plus sign right here. That is for adding chart elements. And I'm going to need a trend line. So I'm going to click on this and go to more options. And once again, we have a trend line, but we really need a polynomial trend line. So I'm going to click on this. This is an order 2 polynomial, which is exactly what I was expecting. I want to put in the equation, so I'm going down here and checking this box. There it is. And I'm going to move on over here and find a way to make this a little bit more visible. All right, now it's red, and now it's a solid line. Okay, let's move this up. All right, and so we have to be prepared to recreate this quadratic function. And I'm going to point out that we have 3 coefficients. This is really y equal ax squared plus bx plus c. That's the general form of a quadratic polynomial. Now, at this point, I don't really need 170 rows in my file. I know that my independent variable just goes from 0 up to 23. And my dependent variable, all I have to do is program that in using Excel. So let's go ahead and take a picture of this for convenience, and then we'll go on over to a new tab. I like to keep track of what I'm doing, and so I'm going to name this tab. I'm going to double click there and enter sample because I know that this is my original data. Now I'm going to click on the plus sign and I have a new tab and I'm going to call it quadratic. Okay, and so I can just go ahead and paste that and reduce the size a bit. Okay, and I know what to type. I'm going to need an A coefficient, a B coefficient, and a C coefficient. I like to make them look like variables, and so that looks a little better, more mathematical. I know that A is the coefficient on x squared. That's negative 0.1375. B is the coefficient on x. That's 4.853. And C is minus 6.8106. Great. All right, and I want to name this function. I'm going to call it f of x. So f of x is equal to ax squared plus bx plus c. Okay, I like to make my functions look like real mathematical functions, and so we're going to switch into Times New Roman here. Okay, there. Now it looks like math. We also need one more function, and that is the derivative, of course, because this is calculus. We need f prime of x, and that's easy. If f of x is ax squared plus bx plus c, then we know that f prime of x has got to be equal to 2ax plus b. You can check me on that. All right, and now it's time to just enter the values. We know that our independent variable is the hour, and we're going to call that x. And then we have f of x. And we have f prime of x. It's pretty easy to enter x because that just goes from 0 to 1 all the way up to 23. Okay, and then f of x is equal to a, which is $f, $3, times x squared. That's a2, and then we indicate a square by putting that little caret with a 2. We have to add b, which is $f, $4, and that's times just x, a2. And then finally, plus c, $f, $5. Okay? Now we need f prime of x. That's equal to 2 times a, $f, $3, times x, which is a2, plus $f, $4. That is b. Okay, and I'm going to take these and drag them down. There we go. And now, finally, we can get a look at all three of these together. I'm going to highlight all three columns and go over here and open up a scatter diagram. This time I'm going to use lines. Now this one looks funny. It looks like you're going to get 3 lines, but if we click it, we're going to get only 2. Now we can look at f of x and f prime of x together on the same graph. And it's pretty clear that we have a maximum right here. Remember that a polynomial can only give you one extremum. It can give you one minimum or one maximum, and in this case, we wound up with a maximum. And there it is. It's kind of hard to tell exactly what time it happens, but it looks kind of like it's 5 or 6 in the afternoon, which makes a lot of sense. And then we also know that at this point, f prime is equal to 0 because the tangent is horizontal at that maximum. So let's go on over to our data and figure out where this happens. Okay, so at the beginning, f prime is positive, right? And then the slope goes down gradually. And then eventually it crosses the x-axis and becomes negative. And so sometime between 5 o'clock and 6 o'clock in the afternoon, we reach our maximum. We have a horizontal slope. And so this really makes a lot of sense. According to this model, pizza searches reach the maximum frequency around this time. So people are getting off of work, they're finishing what they're doing for the day, and they're thinking that they don't want to make dinner, they would rather order out. All right, so this is very believable. Okay, what happens if we decide that we'd like to have a more detailed graph? I mean, this is okay. This quadratic polynomial is not too bad, but if we look closely at it, then we can see that there's a lot more detail that we could be considering in this graph. For example, it really looks like there's some up and down around lunchtime. It's kind of funny. There's some activity very early in the morning. Maybe some people are partying. And then it goes way down, and then it kind of comes up like this. And I don't know. It looks like the curve is doing more than just maxing out in the afternoon. It looks like there's something that happens around lunchtime and, maybe even very late at night. And so we might look at this and say, wow, I really don't think that a quadratic polynomial is telling me everything that I'd like to know about my data. What about having a higher order polynomial? We already know that, with a quadratic, you have only one min or max. You can have one min or one max, but you can't have any more. Okay, if you have a higher order polynomial, like for example, a 6th order polynomial, then you can see a lot more details. Let's go ahead and take a look at that. We're going to go back to the sample here, and we can take a look at what a 6th order polynomial would look like. And so we're going to insert another one of those scatter diagrams, but this time we're going to add a different polynomial trend line. So there's the same data again, and we're going to click on the plus sign, and once again, we need a trend line, and this time it's a polynomial of degree 6. Once again, we want to see the equation, and we also want to see that trend line. So we're going to change the color and make it solid. Okay, and I think we can make this just a little bit bigger, maybe size 10 instead of size 9. Okay, and it's pretty clear that we now have many more coefficients to deal with. I mean, this is really y equal ax to the 6th plus bx to the 5th plus cx to the 4th plus dx cubed plus EX squared plus FX plus G. Oh my goodness. Okay, so we now have 7 different coefficients. Before we had 3 coefficients, and now we have 7 of them, all the way from A up to G. We definitely are going to need a new worksheet. We're going to try to recreate this graph here and study the derivative. All right, so let's go ahead and do the same thing we did before. We're just going to enter those coefficients so we can include the function in our new graph. Okay, A, B, C, D, E, F, G. And A is this right here. Oh my gosh, what is it? This right here. 2E minus 05. That means 2 times 10 to the minus 5 power. And that is 2 times 0.00001. Wow. Okay, so this is really a tiny coefficient. Okay, now we can enter our coefficients. So A is going to be 0.00002. B is minus 0.0011. C is 0.0261. D is minus 0.321. E is 2.678. F is minus 10.623. And finally, G is 15.824. So we've already called the quadratic polynomial f of x. Let's call this new one g of x. And so there it is. G of x is ax to the 6th plus bx to the 5th, and so on. Just like with the quadratic polynomial, we know that we can take the derivative of this order 6 polynomial, and we get this. G prime is 6ax to the 5th plus 5bx to the 4th plus 4cx cubed, and so on. Now it's time to enter everything in, okay? The hour is the same, right? That is our x. And then we have our g of x. And then we also have g prime of x. All right, so once again, x is going to go from 0 to 23. And we can just use Excel functions to enter g and g prime. Okay, so g is equal to a, which is $F, $4, times x to the 6th power. Okay, so that's a2 raised to the 6th power, plus b, which is $F, $5, times x to the 5th power, plus c, $F, $6, times x to the 4th power, plus d, $F, $7, times x to the 3rd power cubed, plus e, $F, $8, times x squared, plus f, $F, $9, times x, plus g, $F, $10. Okay, great. And then g prime, I already know that g prime is going to be equal to 6 times a, $F, $4, times x to the 5th. plus 5 times B, $F, $5 times X to the fourth, plus 4 times C, $F, $6 times X cubed, plus 3 times D, $F, $7 times X squared, plus 2 times E, $F, $8 times X, plus finally F, $F, $9. Okay, there we go. That is our derivative. Now, I'd like to give you an opportunity to double check my formulas. Okay, I'm just going to put the original function. Okay, so this is the function G, and this is formula text B2. Okay, and then we have formula text D2. So you can double check that this is correct. It's kind of messy, but it really works. And so finally, we're just going to pull this down. There we go. And let's take a look at what happens. Now, I mentioned before that using higher order polynomials really does present a problem. This curve doesn't look too bad. Okay, but we're going to find that there's a problem when we try to recreate it. And so I'm going to highlight these three, go to insert again, and once again, we'll try this line chart right here. Okay, so there is our diagram, and it really, really does not look like what we have in this image right here, does it? There are two problems going on. Okay, number one, as you saw, we only approximate our coefficients. So for example, A, we only have the first digit, right? We have the 2, but we don't have the digits that come after it. Probably it's something like, 2.4596, what. There are a lot of digits that come after that 2. The same thing here for this B. We only have the first 2 digits. But the problem is that A is multiplied by x to the 6th, right? B is multiplied by x to the 5th. And these values really get huge. Okay, so if you look at x to the 6th and x to the 5th, imagine what it looks like when you have 10 to the 5th and 10 to the 6th. Okay, so 10 to the 5th is 10,000. 10 to the 6th is 100,000. Okay, and then when you get down here to 23, wow, 23 to the 5th, wow, it's really huge. And 23 to the 6th, well, that's even more huge. And so that means that, if you have the coefficient being a little bit off, then the difference between the curve and the approximation is really going to be quite large. Okay, so this is what we call a numerical problem. There are ways to get around this. We can find ways to get better approximations of A, B, C, D, E, F, and G. We can get 10 or 15 digits. But I really think that the best thing to do here is to use a completely different method. We should use sines and cosines. They really have advantages for capturing this kind of daily behavior. And so that's what we're going to do in the second part of our tutorial. Or when you're dealing with small decimal numbers like we had with the air pollution, then this problem is not so big. But when you have large numbers, then numerical problems can be a big thing. Okay, so thank you for being with me, and I hope to see you in part 2.